All right, let's start. Do you have any questions? Okay. So where were we, right? So we were still kind of around discussing Ito integral and Ito's formula. And so, right, to recap, suppose we have a process that is adapted, right, to the Brownian motion, then the integral, right, the Ito integral, defined, right, as the L2 limit of the Riemann sum, is also an adapted process, okay, with respect to the Brownian motion filtration. And so with that, right, we have the following properties. The first one is generally the Ito integral has expectation 0, and the second moment, which also is the variance, is equal to the following, which roughly is, oh, sorry, the squares inside. Like the quadratic variation, right? Integrated. Second, if we know, right, that we are integrating a deterministic integrand, then we also have that the integral, right, will be normally distributed with mean 0 and variance like so, which, right, is just an extension of property A, but now we know the distribution. And C is what I did not say last time, and what Cesar, right, mentioned in the review session, which is that this is a martingale, right, with respect to the Brownian motion filtration. So let's look at property C a little bit. What does this mean? What this means is that if let's say if t is less than u, right, then you take conditional expectation of this will be u, condition on this, then we will get the integral like this, right? So let's try to understand how this can be true. So, well, for one thing, right, the integral is linear, so we can split it into two parts. All right. Second of all, right, because the integral is an adapted process, that means that this, right, is completely known, right, with respect to this Brownian motion filtration, or this is completely known, right, observing Brownian motion up to time little t, meaning, right, it's just a deterministic value as far as we're concerned, right, condition on the filtration. So you can pull it out, right, without any issue. and then you have this. Which, as we can see, right, is almost our answer. So this is this one right here. So of course, right, if what we say is correct, then this must be 0. So that basically, right, leaves us to wonder how this item can be 0. All right. And actually, that actually is a general conclusion too, in the sense that, okay, fine, we know that this is a martingale, or accepting this is true, right, which it is. We're trying to understand why it's true. But a consequence of that would, or another way, an equivalent way to phrase, right, this result, which is also as useful, is that, right, look at this. What this is saying, right, is that if you start at the moment and go into the future, then in terms of average value, right, it seems like, it looks suspiciously like this property actually. In fact, right, you can think of this statement as a generalization of this statement. Yes, because expectation is expectation condition on the trivial filtration, right? So, and of course, we might expect some generalization of this as well, but that for later. Anyway, right? So this is a nice statement to have. So again, right, as long as we go into the future, right, then conditioning on the present, the average movement, right, of the integral is 0. Now, so why could this be true? Okay, I guess we did not quite explain this either, but well, we kind of said that that's because dw is 0, right? Expectation-wise, we did say that. So again, there's just tons of things to discuss in this class, and my approach for this course is to be more applied, right? I don't want to make it to like a theoretical stochastic calculus course. You should know some, stochastic calc knowledge. But so if you are interested, right, in the mathematical direction, definitely look into it and think of why it's true, right? I mean, of course, this is the intuition, but to work out this intuition into a full proof, it takes takes a few steps. All right. But anyway, I want to highlight that probably, right, something along that line also is true here, except we got to be careful though, right? Because we are conditioning. And you know that conditional expectation, well, in some respects are like expectation, but in some other respects is slightly different, right? Or it's more subtle. So, okay. One straightforward hope is that somehow we can just drop that, right? If somehow we can just drop it, then we can use the result in property A and say that, right? That's 0. In other words, we're claiming that this is independent of the Brownian motion filtration at time t. Whoops, I can't write. Yes, again, that's the thinking process. So now, right, is it true or false? If we can establish this is true, then of course, right, what we say above will be straightforward. If it's false, that doesn't mean that this cannot be true, but it has to come out of a different reasoning. Okay, what do you think?
Is it true?
Do you think it's true? Why would you say it's true?
Because from t to u, that increment is independent of what happened before, like the filtration up to time t.
Okay, that's a that's a nice I don't know, intuition, right? What you're trying to say is that the time motion increments, right, is independent, right? Because it's in the future, so it's independent of the present or the past. Okay, but what about this guy? Right? What about this guy? Now, if both of them are independent of the past, or of, the past up to the present, the history, right? Then that seems to hold. Sure, ground motion does this. Do we know anything about this? So, right, I mean, I did say that it seems to be independent in the discussion, right? So it has some plausibility. Okay, fine. You're saying something along the line of what Kareem said, but what we're asking for is independent. So you need to assert that somehow the original two random variables are independent of the filtration. Do we have that? That's my question. Now here's not quite. So here's a technique that you can use, right? Not in just this question, in general, is that if you are faced with a more complex question, try to come up with a simpler example, a toy example, to test the idea, to see if it works. So what kind of process can we pick to test our idea that is not trivial, so it will not trivialize the question, right? Because ground motion, right? Our choice is on this, and our questions on this. Not quite. You could, yeah, but something more specific. No, not in that sense. This is about independence. It's not about the structure, right? So how structured this guy is doesn't really matter. Okay, good. But what kind of constant? Do you mean like this? It's already, oh, so deterministic, right? Deterministic. Okay, good. So actually that probably, right? So first of all, let's try this. So this is thought process. So if you try a constant, then you get this. All right. Is this independent of the ground motion filtration? Right. This case is yes. All right. Then next, what Eugene was suggesting, right? Something like this. So now, right, is this independent of the ground motion filtration? How do you know? All right, you think yes, but it's hard to say, right? It's hard to say. The answer is actually yes, but if you want to show it, you either, because right, actually, when you do this, you take away the stochastic nature of this guy, right? So the only randomness is on the ground motion, which already is inherently independent of this. So here, right, I want to present a way to analyze this using Ito's formula that basically highlight the use of Ito's formula in some context, right? You could prove it in some other way, but let's explore this using Ito's formula. Why Ito's formula may be useful here for the second question. The reason is, Ito's formula will turn this into what? Into a explicit formula plus some Riemann integral. So hopefully, right, when we do that, we might have something easier to analyze. Who knows, right? I mean, I might be off the chart here, but let's try, right? So the whole point of Ito's formula is we need to come up with a function, right, of t and wt to differentiate. And we try to match that with the Ito integral we have. Okay? So what function do you think we should try to match with this? What function do you think we should try to match with this? No. I mean, it's a function of t and wt, right? So e to x meaning what? E to wt. If e to wt, you won't capture this. E to the t, you will not capture wt. Well, I guess, how about both? No, nothing to do with black church. It's just this, right? Because it will capture this part and this part. So let's see, right? This will be e to a t dwt plus e to a t et. Sorry, what am I saying, right? So differentiate with the t, yeah, e to a t wt et. So maybe I should try the other way first. So e to a t wt et plus e to a t dwt, right? Where y, the function is what? F of tx is e to t times x, right? So the derivative with respect to t is this. Derivative with respect to x is just e to t. There is a second derivative, right? But the second derivative is 0. Okay, so that's the Ito's formula. So what that tells us is the integral, right, from t to u of e to the s, sorry. So e to s, how's it? Sorry. So if we integrate from t to u, right, of this part, we'll get the difference. So we'll get e to u wu minus e to t wt will be equal to the integral from t to u of e to s ws ds plus the integral from t to u of e to s dws. Okay, so far? Is this okay so far? All right, so again, in case you're lost, right? What we're doing is we want to investigate whether this is independent of the ground motion filtration. So what we try, right? What we try, again, I may fail here, but one noble attempt is to try to somehow rewrite this Ito integral, okay, as a function of the ground motion with some Riemann integral. It may or may not work, who knows? The idea just crossed my mind, right? So here, what we have then is the Ito integral then is this minus this minus this. Okay. Now, is this independent of FWT? Did we accomplish anything? Does this look any easier to analyze? This is the question. Well, not quite, right? This doesn't look any easier to analyze. But, right, here's the thing. There's one more step because I know what I'm doing. That this will make it, this will get it home. What I'm trying to say, right, is this is just playing around, right, to analyze this question. Again, right, the answer you expect would be yes. The reason simply is that because this term is independent of the past history, right, because you're doing from T to U. Except that this argument is a little bit abstract because you have to now invoke the limit of the Ito integral, right? And again, right, if you're into Rieger's argument, then it's okay, right? But it may not be super clear. A way to get around that is to use Ito's formula to turn this thing around. Is a little bit more advanced, a little more mysterious, into something we know. All right, it's just mathematical thinking. It may or may not work. Okay, it may or may not pay off. So the reason, right, is let me ask you several things. Is this guy independent of FWT? Is this guy independent of WT? What do you think? Is a no on both. Why is this a no? The reason is, right, you may be tempted to think of U minus WT is independent, which is true. That's the property of ground motion. But after you scale it, yeah, it's not gonna remain like that. Okay? So the answer is no. What about this? This is actually easier. This is because WS is still related to the ground motion T, right? Because this is, yeah. And so integrate, this is deterministic, right? So that's actually the advantage of turning it to the Ito integral, to the Riemann integral. Because then, right, all the analysis, this is like summing, right, terms. So this guy is dependent. So when you sum it up, there's no chance. Okay. But that doesn't mean that when you subtract them, right, nothing interesting can happen. So we can still have hope. But what's the hope? The hope is in this term right here. We want to make it independent of the ground motion, right? How can we do that? We can do that by the classical trick of add, subtract. Yes? Now, this piece will be independent of the WT. Why? Because now, right, every single piece is independent. So when you add up, it's independent. Now, someone tell me what this is. What is this? This is e to the u minus e to the t times wt, right? Because, wt is a constant in terms of s. So you can factor out and you just integrate the exponential term. All right. So going back to the original piece, what are we doing? We're having this piece subtracting this piece. So what you have is, right, now you see some miracle happens. When you subtract, right, what you have is e to u wu minus wt. All right. And then these terms, which are supposed to be dependent on this, miraculously cancel out. And what you have left is and this now is clearly independent. You understand? Any question? So, right, the above is just a calculus kind of techniques of demonstrating, right? I think, again, it's really a long way to justifying this. But, if you want to use Ito definition to just justify this, you also have to be a little bit careful. On the other hand, I think it's not totally useless because you guys are new to Ito calculus. So seeing all these, right, techniques is helpful, right, to understand. So it is a tool you can use, but the calculus I've been doing so far, right? I've just been doing calculus, really, nothing more. Okay. So to recap, the answer here is also yes. So our thought experiment on this guy, right, so far works with constant and only depend on us. But that doesn't cover everything, right? We need something more interesting. So what else? Actually, now that this occurs to my mind, I think Fatima's suggestion is not bad. WS, I think that's what she suggested. Why? Why is not so bad? Actually, why is good? The reason is you know explicitly what the right-hand side is. Why do you know this? Because of Ito's formula. So it is exactly something like the above. Correct. So someone tells me what this is. What's the answer here on the right-hand side? No, Jingmei, that would be from 0, right? We're not going from 0. Yes? We're not going from 0. If we wanted to go from 0, you're right. We're not going from 0. So what's the answer? Oh, that's even further from the truth. Of course not. It'll be that. Sorry, should be u minus t, right? Because you go from t to t. Yes, you see this? Again, how is Ito's formula? You could do that, or I will just do it straightforwardly, right? So first of all, this still holds. Right? This still holds. But pay attention that you are integrating from t to u, right? So you may not be used to this, but so you're integrating from t to u of this. Right? And what is this? This is this. This is this. And this is this. Got it? All right. Now, is this independent? Right? So obviously, it's all about this term because this is a constant. Is this independent of FWT? Is this independent of FWT? Oh, you think yes? How would you know? It should be a no. All right. The reason is this. You could do this. Now, this piece is independent, but this is not. Okay. So you should not. Now, generally, what can you do? You could test the covariance with, you could try this. And you know what? I'm willing to bet that it's not going to be zero. It can't. All right. Now, I'm not trying to say that this is an easy calculation because you're doing something like this, third moment. But it's not that hard. You can try it. Okay. So, no. So, no, right? This is not independent. No. So, this is independent, but this is not. Okay, this is not. It's not independent. All right, you don't seem too convinced. Let's try this. How will you calculate this? Right? What is this? How do you calculate this piece? This would be zero, right? Why? Because, I mean, in some way, it's the covariance of something with itself, but you can try this. right? And this is 0, and this is 0. Odd moments of the normal. How about this? Right? Now this is 0 because of this. So we need only to calculate this. Now we went through this exercise before, right? How do we calculate this? How do we calculate this? Yeah, right. So we would add, subtract, right? Well, so first of all, let's see, right? This will be like this. You know what? Here somehow it is 0. So I'm in an unlucky moment. Because here it would be something like this. And yeah, it's somehow they have a moment here. This is 0, 0, 0. So actually this is 0. So I'm unlucky. This is 0 actually. Yep. It's not really odd, right? But actually that doesn't prove that I'm wrong though. That doesn't prove that I'm wrong. You know why? Because this is about independence, right? So even though this is 0 by the calculation below, that doesn't mean that I'm wrong, right? What can I change to still turn this around? What can I change to turn this around? I could try this. Okay. I could try this to be WT squared. The reason, right, is independence is a tall statement. As long as I can find something that is non-zero, then, right, that will be a false. Okay. So again, I think let's not repeat the calculation, right? Trust me, if you want to go through a calculation, we can try to do it after class, but it will not be independent. Okay? It will not be independent. So we can try this, but let's not. And even if this goes through, okay, I don't think it will. I have an easier statement. All right, so last attempt. The last attempt I'm thinking of is try something like this. You pick an integrand that is not moving in S. Why? Because now this guy will be just what? Okay. Now, I hope this will not be independent of FWT. All right. So this part should be cleared as a no because of WR. Okay. So basically the point is, right, that's a bunch of calculations. That was fun. The point is, this is a false statement. That's not true. Okay. So does that mean that, right? So what I'm saying is, remember what I said, right? Even though this is false, doesn't mean that this cannot be true. This can still be true, right? This can still be true. How, right? How is, for example, notice that the calculations we've done below, if you try to take the integral and you take the conditional expectation of these guys, you will get 0, right? You will get 0. So then, even though they're not independent, oh, sorry, no, these are independent because I used the example. For example, actually here, right, this example. If you take the conditional expectation of, where was I? This guy, right, with respect to ft, you will get 0 because basically you just take conditional expectation here, right, of w squared and something with it below. So it's still true, right? And maybe let me just try this. Okay. So it is still true that the conditional expectation will be 0, even if the integral may not be independent of this. Okay. How? Let's look at 2 examples. The example of this, which I claim is not independent. All right, you can check, but it's not. This guy, right? So what is the conditional expectation here? So to do this, right, all I have to really do is conditional expectation of this guy, which is conditional expectation of WU square, right? Condition FT. Well, we've done that above, right? In some way. So let's redo it. But so this is going to be WU minus WT plus WT, right? Which will be all right. And then plus WT squared. The rest will be 0, right? You split this, you got this to be independent of this, so it becomes expectation. The cross term will be 0 because this is 0 expectation, and then this will be this square because it's FT. So it will be U minus T plus WT squared. So you see, when you add this up, it's exactly 0. All right, so that's the first one. This one is the same way, but that's more interesting. Oh, not more interesting, it's the same. So now if I fix a time, sorry, TTU. So if I take conditional expectation, right? I can also do the add and subtract trick. But actually, if I do the add and subtract trick, it's kind of weird. No, it's fine, right? Because if I add and subtract, what do I get? WR minus WT, right? WU minus WT, like that. And then plus WT times expectation of WU minus WT, condition of WT. Right? So basically, I add and subtract WT here. And I drop the conditioning because both of these terms are independent of FWT. Here, right, I factor out the WT because it's conditioning, and then I have this. And again, right, by independence, I get this to be 0. Okay. So again, the conclusion is the conditional expectation can still be 0, even if this may not be independent. All right. So how is that so? I want to give the last kind of intuition on why this is true. And that kind of is, the clue is something like this. Okay, the clue is something like this. So here we did the add and subtract trick. It turns out that there's another way to look at this. Which is by the so-called independence level. Do you remember what that is? Or did you learn that from Math Finance 1? So the independence lemma is this, right? That if you have two random variables, x and y, all right, and then y is independent of the filtration, right, generated by, hold on, let me try to think. Y is independent of a filtration, and x belongs to that filtration, then expectation of phi of xy, right, given phi, will be basically you plug in the expectation like this. All right. So what it says is this, that when you take conditional expectation, you have two random variables. One of them is independent of the filtration, and the other is like a constant with respect to that filtration because it belongs to that filtration. What you can do is you can literally just make the other one a constant and take expectation, okay, with respect to y, and now then plug back that constant after you find the expectation. So you know what? I don't think that works here. I was trying to say that this situation is like the independence lemma, where this is independence of this filtration, But yeah, I don't think I'm right because this does not belong to this filtration, so that's not true. No, that's not true. Sorry. I guess the reason is more complicated than that. Anyway, maybe let's not go further into that. So I guess the proof for this is, in general, is more complicated. The proof that this thing is zero, right, is more complicated than I thought. So basically, okay. So the takeaway message is this, right? That the integral here is not independent of the filtration from the history. Okay, but when you take expectation, you can still get it equal to zero. Yeah, I think the proof, if you want to do it rigorously, it's much more complicated than what I try to attempt. So sorry about that. Okay, so that's a long-winded discussion on some ways, okay, to see that this is a martingale with respect to this filtration. I don't have a reason. I don't have an easy reason to show you. I don't have an easy reason to show you this is true. If I were to do it, it will be the same as proving this. All right, it will be the same as proving this, which is complex. All right, so sorry about that. Okay, questions? All right. So sorry, this does not apply. This is still true, but it doesn't apply to in our case, actually. This is irrelevant to this. Right. So it's true, but that doesn't explain the math. You know what I mean? It doesn't explain the math because you're saying that the wealth is a martingale, right? But it's circular reasoning, right? Because I mean, the wealth is a martingale exactly because of this reason, right? So you gotta independently prove it somehow, right? You can't go around, you know what I mean? So basically, the big result is this: that the integral with respect to a martingale is still a martingale. That's a big result, but I think I cannot wave my hand through it or give an easy proof of this. You really have to go through the martingale math, all right, which I don't want to go into. Okay, so let us now maybe try to explore Ito's formula some more. All right. So I was explaining Ito's formula last time, where first of all, right, this is Ito's formula. And the intuition, right, is that as t goes to t plus dt, then wt, right, goes to wt plus dt, right? And so when you measure this, what you're doing is you're measuring the change of the function as t goes to dt, right? So you see two movements. You see two movements. First is a movement in time, and second is a movement in space. But both of them is via, right, time move, right? So time is the principal mover here. Time moves, then ground motion move, and then F moves. Anyway, but if you try to split the view, right, if you try to split the view, in other words, if you were to do calc 2 or calc 3, actually, right, then basically this is called the Taylor expansion. Then you get f sub t, right, times dt plus f sub x times dx. And then you can go on, right, plus, let's say 1/2 f sub xx dx squared plus 1/2 f sub tt dt squared plus, I guess there's only x sub t dx dt, right? And you can go on as far as you want, as long as f is differential. So actually, this is approximately, it's not equal, right? But basically, it says that if you want to approximate the change, right, you start with the first term derivative, and then you go to higher order terms, right, with the appropriate partials and with the appropriate division. So we see that, right, the Ito's formula is nothing but Taylor expansion plus quadratic variation, right? Plus quadratic variation, because dw quadratic variation is the t, right? We explained that. So what I try to say, right, is, so maybe just one thing real quick is this, right? Let's try this in calculus 1. Or, I mean, classical calculus. Suppose you only have a function of one variable, right? Let's say this. Okay. Then, right, you can also do the same thing, f sub t dt plus 1/2 f sub tt dt squared, etc., right? And plus higher order terms. So in fact, this is again the Taylor expansion. And if you recall Taylor expansion, right, I mean, it goes on forever, right? It goes on forever. So now, well, I mean, for example, right, you can see that e to the x is 1, right? Plus x squared over 2 plus x cubed over 3 factorial, so on and so forth, right? This is the classical formula for e to x, but, right, it comes from the expansion, right, of e to x around x equal to 0, right? So you see, this is e to x minus e to 0, right, is equal to x minus 0, right, times, basically, because the derivative around 0 is 1, right? So you actually don't see the derivative at all, right? You just see the dx squared, etc., right? Now, the thing, though, is this, that when you look at a fundamental theorem of calculus, though, then you have that the f of, right, I don't know, f of u minus f of t is the integral from u to t, right, from t to u, f prime of s ds. Okay. So in other words, fundamental theorem of calculus says that df, right, is f prime dt. We saw that before, or f sub t. Maybe I shouldn't do f sub t, right? Because he is only one variable, so it's f prime, f double prime, that kind of thing. But so what I try to say, right, is kind of reconciling these 2 points of view. The first point of view, right, says that approximation-wise, you don't want to stop at the first derivative, right? You can go on forever. And the more, right, the more you do, the better the approximation is, right? So if you chop off the approximation here, you get an okay approximation of e to x around 0. But if you go further away, right, this will be pretty bad. Or, conversely, if you keep adding terms, right, you get closer and closer to e to x, even if you're around 0. On the other hand, right, when it comes to integration, though, right, then you only use the first derivative term, and you discard, right, any higher power terms, right? You discard any higher order terms. So while why these 2 points of view? Okay. Why these 2 points of view are consistent? Well, I guess, right, I already told you this before, so let's not pretend that it's really a big deal. bt squared is 0, or et raised to any power that's higher than 1 is 0. Okay. So, but what do we really mean, right, by this? The meaning is this, that if you were to take the integral, right, from t to u of a function, any function, ds raised to 1 plus epsilon, that would be 0 for any epsilon. Meaning that if you take the sum and you take the limit, you will get 0 for any epsilon. All right, and you can test it. You can test this. Okay, so when we say something like this is true or something like this is true, what we mean that is true is true in an integral context, or is true in the limit of a Riemann sum like this. Okay, and so therefore, right, even though, right, in the approximation we get this, when you integrate it, right, when you integrate both sides, what we mean is you keep continuously adding these terms, then only this one contributes, right? All the other terms contribute nothing when we sum it up continuously. Does it make sense? So now going back to, right, the higher dimension point of view. In the higher dimension point of view, it's the same thing, right? So this is the difference point of view, right? The difference point of view. And from the difference point of view, you can pick up as many more terms as you like to improve your accuracy. But when you start to add things back, right, continuously, when you start to add things back continuously, then, right, only some terms may be feasible. For example, if you literally take this as dx, then the x squared will be 0. The t squared will be 0. The x et will be 0. All right. So when you sum up continuously, then in classical calc, right, you only have two integrals, this and that. Okay. The other ones are 0. So how about the Edo's formula? Well, for the Edo's formula, right, you see the situation is like the high dimensional calculus situation, except that when it comes to a higher order term, because, right, w is not an x, right, w doesn't move independently with respect to time. W indirectly depends on time, right? And therefore, this is not really a dx. It's really dwt as t moves in time. And this guy is so rough that, right, when you square it, you square the change of it, you still see something visible. So therefore, right, this guy shows up. But on the other hand, right, any other terms like dt square, or what is this? This is dw dt. Is also 0. You don't see it. Okay, so any higher order term, when you continuously add, you won't see it. So they always appear. So that's the reasoning behind U small. So this disappear, this disappear, this is visible. All right, because this is not just dx, but it's dw, which indirectly moves with respect to time. Any question about this? Okay. So maybe let me ask you this, right? How do you really check the statement dw dt equals 0? No, no, right? It's not that. It's not in that sense. The reason is, right, for example, when I say dt squared equal to 0, right? Does that mean the expectation of dt squared equal to 0? I mean, yes, but that's not, it's not in that sense, you know what I'm trying to say? So, sorry, dwt, right? It's not in that sense. Because dt square, right, when you take expectation, it's not clear that it's equal to 0, right? Where does that come from? Again, right, the test is by, right, the integral, right? So what really is going on is I claim this. Meaning that the sum is 0. Okay. And when you look at this, right, I hope that you see it's not a trivial statement. Why? Because if you drop this, then that's not 0, right? That's your integral. Right? If you drop this, then it is also not 0. It is your Riemann integral. But if you combine the two, then the variation is small enough that force the whole sum to be 0. Okay. And like Cesar mentioned, right, in the review session, the reason is basically, roughly speaking, this is square root of dt. You need the absolute value here because dw can be positive or negative, right? So like that, or right, as we say, dwt squared is dt, right? So basically, dwt dt in absolute value is like dt to the 3/2. And like I said, right, dt raised to anything higher than 1 will be 0. All right. So again, I'll let you play around with this idea in this week's homework. Any question? Okay. So let us continue and discuss more in general. So you might think that what we said above is general enough, but not quite. We need one more. And then for that, we need something, basically, it's a technical term called Ito process. So X is an Ito process if basically it can be written as a Riemann integral and a Ito integral. All right. So basically, well, many things are an Ito process, right? So you may wonder what is not an Ito process then? Right? Because holy cow, right? Anything like this is great. Well, it may be surprising to you, but there are things that are even worse than this. So a non-Ito process would be something like something you will see later on. And this is exactly the reason why the theoretical analysis of exotic option may be hard. A running max. All right. The running max of the Brownian motion cannot be represented as an Ito process, meaning the running max is so irregular that it cannot even be captured by a Brownian motion, Ito. So that is something else, all right, that we'll look at later. But so for now, a lot of things we'll look at will be Ito process. But so what we're concerned with is like this. So now if you have an Ito process, and then now we chuck that into a function. We want to differentiate it. How does that work? And by the way, right, the most friendly Ito process you want to think of is the Black-Scholes model. All right. But anyway, so if you have an Ito process, right, how do you differentiate it inside a function? So this is the chain rule for Ito process. Well, actually, it will be very familiar. It's just an extension of the previous formula. First of all, you still have this term. You still have this term, but now it's going to be dx. And then you have the second derivative, but now with the quadratic variation of x. And here you got to be careful, right? This is no longer dt. This is not dt, all right? So you could leave it like this, but if you want, right? So you can expand this. dxt is alpha t dt plus beta t dwt, right? So this is this guy right here because of that. What about this? Anyone care to guess what this is? What is this? Well, so first of all, right, it's like this. All right, you can think of it like that. And so what is it, right? So it will be, right, this guy above here squared. Yes, right? Now, and then you can just expand it. And right, notice that this is 0, this is 0 from what we said above. So it's just any question? Oh, sorry, right, beta t squared. Yeah. All right, so an example of it now is, now we can solve the Black-Scholes problem, right? Meaning that, I mean, we kind of have enough tools before to check that it's consistent, but now everything we can fall into place. So first of all, let's start out with the percentage, right? Return. This, right, is a SDE, stochastic differential equation, right? This is a stochastic differential equation because the movement of S, right, is captured by a movement in time, a movement by motion, but, right, the integrand also involving S. So that's why it's a SDE. Now, how do we solve this? You know, if you have ever taken ODE, which you should, right? You learn that there's no real technique, there's no universal technique to solve differential equations, right? It's basically whether you can be lucky enough to find the antiderivative. If you can, great. If you don't, then you can abstractly argue that a solution exists, but you cannot write out a formula for it, etc. Here we can, right? We know that. But how do we go around this business? How you go around this business is somehow try a different function, try differentiating the log. Well, why do you do this? Well, if you follow the model, right, you know we want to deal with the log returns. But mathematically, you kind of also have the motivation because you do this and you divide by ST, right? This comes from the idea that if you differentiate natural log, you got basically 1 over x dx, if you will, right? So that's this and this. But now, right, if you apply Ito's formula on this guy, by the way, that Ito's formula, because, right, this will be the Ito process. Then you get, right, 1 over st dst minus 1 over st squared, sorry, 1/2, right? dst derivation. Right? Now, but witness a miracle, because when you do this, basically the st in here cancel. The st square, right, the derivation of st is sigma square st squared dt. Again, canceling. So when all the dust settles, you got mu minus 1/2 sigma square dt plus sigma dwt. Exactly the log return model. Okay. But now this is perfect because this is no longer an SDE. Why? Because the right-hand side does not depend on anything on that. So we're very happy. We can integrate both sides. D, right? By the way, right, I'll just integrate the right-hand side real quick because there's no need to pretend I need to integrate it. Like that, right? Oh, by the way, because I should subtract, right? I should subtract 0. I should subtract W0, right? But W0 is 0. So there's nothing there I need to do. The left-hand side is log ST minus log of S0. Exponentiate both sides. And I get my explicit form. So these 3 steps process, 3 steps formulas exactly is the whole glorious application of Ito's form. Any question? All right, so that's all I have for today. If you have any questions, I'll answer. If not, I'll see you on Monday. Yeah, thanks. Right, in 2 weeks, no, not 2 weeks, right? 1 week and a half, right? 20. Yep, the Monday after next. Yeah.